Now we will turn our interest to the factorial function, which I have defined in two different ways. The first one illustrates a recursive process. Factorial is recursive. The last one illustrates an iterative process where we have a tail recursive call. So first let us see what happens when we call fac4, which is of course 24. Now let's follow the call stack when we evaluate fac4, and we see that fac4 calls fac3 here, and fac3 calls fac2, which calls fac1, which calls fac0. Notice that the multiplications that we have here are pending. They're not done up the stack, but down the stack the multiplication take place. So first here we get a contribution by 1, because when n is 0 we get 1 as a result. That's the bottom of the recursion. Following that we get 1 multiplied by 1, and we multiply by 2, we multiply by 3, and we multiply by 4, which ends up in the final result, which is 24. So in the middle of the recursion, when we encounter the turning point, we see that we have used a lot of stack space. Actually 4, 3, 2, 1 and 0 have all been enumerated in entries in the runtime stack. And what happens down the stack is that these stored numbers on the stack are all multiplied and we get the final result. Now let us turn our interest to the other variant of the factorial function, which immediately applies a helping function where we accumulate and calculate the result in the second parameter. So fac1 calls itself recursively, but instead of multiplying the result of the recursive result as in the upper variant, the result is accumulated here. So we multiply n by r, and it means that we eventually ends up with the result in the second parameter, and when n becomes 0 we have the result in the second parameter. Let us see how the stack develops in this case. So we have the call to fac1 here, and let us see how it develops. It calls itself recursively, another recursive call, until we reach the bottom of the recursion. In this variant of the factorial function, the multiplications occur on our way up the stack. So it means that when we reach this point in time, we have the result here in the second parameter. Now what happens down the stack then? Actually nothing. We just bring this result down and get it out ultimately here as a result of our function call. Again, in this way of illustrating the development of the stack, we have a lot of stack space here as before, and it turns out that this part of the stack is actually not used for anything at all. So therefore it is possible to make an optimization. So let's see it again. Instead of growing the stack, we can reuse the one and only stack frame. We see it here. we reuse the stack frames and we accumulate the result in this variable. Until this point in time, we are done. We have the result here. So the result of 4 factorial is 24. So please notice here, this is the end of the game. There is not a lot of stack space used. We have only one stack frame, and the result is here. The last variant of the factorial function implements an iterative process. So it is iteration by means of recursion, by means of tail recursion. This call of fact1 is a tail call, because when it is called, nothing happens on the result of fact1. So this is a contrast to this call, where there is a multiplication taking place on the recursive call. Here, when we come back with a recursive call, we are done. Tail recursion relies on tail calls. So here we will train ourselves to recognize tail calls. So here the function g calls a function f. F is a tail call if g returns the result of f directly. That is, if there's no pending calculation done on the result of f. In Scheme, tail calls must be implemented efficiently as jumps, as gotos. What is important to notice is that the stack frame of g is discarded when f is called. It is not necessary to keep the stack frame of the call of g when g calls f. So Guy Steele phrased it in the following way: tail calls are gotos with possible parameters. That's an interesting point of view. Now let us take a look at some small scheme functions and identify tail calls. First, in the function a, b is a tail call because there's no pending calculations going on when b returns. So when a calls b, the stack frame of a is discarded before we call b. In this function, we use a special form if either g or e is called, and both of them are tail calls, so there is no need to keep the stack frame of c when either d or e is called. This is a variant and is not a function in Scheme. It's a special form, and it is transformed to if in this way. And here we see that the call of e is a tail call. There is no need to maintain the stack frame of c when e is called. H and I are non-tail calls because when we return with the results of h and I, they are used by g. G, however, is a tail call. Relative to f, we can discard the stack frame of f and replace it with g, because nothing happens in f when g returns with a result.